At this point, what about the renormalization of the quartic coupling? And by quartic coupling, I'm referring to the constant lambda in the action s equal to 1/2 d phi squared plus m squared phi squared plus lambda divided by 4 factorial phi to the fourth. So now we are really interested in the renormalization of this constant here, lambda, related to the quartic coupling, quartic interaction. Now, to one loop accuracy, we have to consider the following Feynman graphs. In particular, let me sketch them. So here we have an edge that I have dashed, and this represents the field phi 1. Here we have a loop, and the loop is split into two edges. So here we have two edges, one edge here and one edge here. Then we have two vertices, and here the vertices are 4 valent. So here we have phi 1, phi 2. You can see that from the vertex we have 4 edges that are coming out. In particular, they are four parts that are coming out of the edge. And similarly here we have phi 3, and then we have phi 4. But we also have other two possible graphs if we change the labeling of the external edges. So in particular, let me do the same thing. Here I'm dashing this line here, but this will be phi 1, and then phi 1 will be paired with phi 3 instead of phi 2. Therefore, here on the right we have phi 4 and phi 2. And similarly, we also have another possibility because we can pair phi 1 with phi 4. So here we have phi 4, we have the loop with the two vertices here, phi 3 and phi 2. So these are the corrections, the one loop corrections to the 4 valent vertex of this kind without any loop. So here we have the vertex, and we associate to this vertex the constant minus lambda minus delta lambda. Remember that in our theory we are also considering this correction to lambda that we call delta lambda, and according to a certain renormalization scheme that we have to choose, we can set the value of delta lambda and in such a way that the calculations that we do not lead to infinities. These delta lambda corrections, together with the corrections that we call the delta m squared and delta k, that we considered in the previous lectures, these are corrections that arise because we are integrating out some fields, in principle some high energy fields, the high energy contributions, or actually we could also integrate out the low energy contributions. So it depends on the way we think of these corrections. Now let's consider this first graph that I have sketched, for example. Here we can assume that this field here, to this field phi 1 we associate momentum k1, then to the field phi 2 we associate momentum k2, to the field phi 4 we associate momentum k4. In this case we can represent the momentum pointing towards phi 4, whereas in this case we can represent the momenta in such a way that they point towards this vertex. But this is a choice. And here we have k3, and this is, as I said, k4. So due to momentum conservation, we have to impose k1 plus k2. The momentum that's entering this vertex should be equal to the momentum that's exiting this other vertex. So we have k3 plus k4. But if we call, for example, here inside the loop, we have two edges, as I said, and this is the orientation that I'm choosing. In particular, here we will have momentum p, and I'm just calling it p. It's just a label. And here I'm labeling this as q. We also know, of course, that k1 plus k2 should be equal to q minus p. Q is exiting this vertex, therefore, Since these two are entering the vertex, the summation is equal to the total momentum that's exiting from this vertex. So we can either write q minus p on the right, or if you want, you can also write k1 plus k2 plus p. That's the total momentum that's entering this vertex. That's equal to q. That's the only momentum that's exiting the vertex. But of course, it's the same as this equation here, so nothing changes, right? And from this equation, I actually want to solve it for q. So q equal to k1 plus k2 plus p. And the integral that will arise from this graph is the following. So since we have these two vertices, to the vertex I will associate the function, the constant, minus lambda. In principle, I could also have minus delta lambda because it's a correction to the constant that we have. But this delta lambda, since these vertices are 2, remember that we have to square this constant. So since we square it, and we are assuming that this delta lambda is a higher order correction, we will neglect the fact that we also have to subtract delta lambda to minus lambda here. So we are just considering lambda here. So we have minus lambda squared, which is of course just lambda squared. And we have to divide by the symmetry factor of this graph, which is 2. So we divide by 2. And then we have to integrate. I will specify the integration later. But we have to multiply the two propagators related to these two edges. So the functions of the edges. And the functions are 1 over p squared plus m squared. And then I have 1 over q squared plus m squared. But now, how do I have to integrate this? In principle, I have to integrate over q and over p. So I have integrals of the following kind. D to the fourth q, d for q divided by 2 pi to the fourth, and d for p divided by 2 pi to the fourth. But remember that q should satisfy this relation. So in principle, here we also have a Dirac delta. But instead of writing the Dirac delta and then integrating the Dirac delta, we can simply substitute in place of q the expression that I have written there. So in particular, the expression is, let me do it, I have p plus k1 plus k2 squared plus m squared. And now I am left with just the integral over p. So I just have to integrate over p, divide by 2 pi to the fourth, and this is the expression that I get. Now, to this integral, we also have the contribution given by the other two graphs. This one here and this one here. So I have to add to this integral lambda squared over 2, integral over d4p over 2 pi to the fourth, 1 over p squared plus m squared. And then remember that in the second graph, I have associated phi 1 with phi 3. So I have 1 over p plus k1 plus k3 squared plus m squared. And similarly, in the last graph, I have associated k1 with the k4, or phi 1 with phi 4. So the final contribution would be lambda squared over 2 integral d4p over 2 pi to the fourth, 1 over p squared plus m squared, 1 over p plus k1 plus k4 squared plus m squared. And then at this point, I am going to assume that we are going to integrate over mod of p smaller than lambda 0, as usual, but we will assume that this is also greater than some lambda 1, such that lambda 1 is much greater than mod of kj, where j can be either 1, 2, 3, and 4. So if we make this assumption that the three integrals above, since p in particular its mode, but we are going to assume that in the denominator this is approximately the mode of p squared, and similarly this will be approximately the mode of p squared, and similarly here this will be approximately the mode of p squared. So basically we get the same contribution, which is 3 over 2 lambda squared integral d4p over 2 pi to the fourth 1 over p squared plus m squared, and this will be squared, right, because these two factors are the same in all the three integrals. So at the end of the day, we will have to let lambda 0 go to infinity as usual, and lambda 1 go to 0. When we let lambda 1 go to 0, what we are basically doing is we are implicitly assuming that the external momenta, k1, k2, k3, k4, are negligible with respect to lambda 1, right? But we will take these limits later, and this integral can be computed. So first let's compute the integral without doing all the steps, but the way to compute the integral is this. So this is equal to 3 over 2 lambda squared. We use spherical coordinates, so when we go to spherical coordinates, just like we did in the previous lectures, we will have the integral over the solid angle in 4 dimensions, and the solid angle in 4 dimensions, if you recall, is equal to 2 pi squared. There is also a video in the appendix, let me remind you that, so if you are interested, just check out the video. And then here we have an integral from lambda 1 to lambda 0, p cubed dp divided by p squared plus m squared squared. Now this is a simple integral to carry out. You can make a substitution, for example, of the following kind: p squared equal to m squared u, and you can calculate this integral. It is just something that you do in a single variable calculus, so I'm not going to do it. And the result that you get is the following: 3 lambda squared divided by 32 pi squared, and then you have natural log of lambda 0 squared plus m squared divided by lambda 1 squared plus m squared, and then you have plus m squared divided by m squared plus lambda 0 squared minus m squared divided by m squared plus lambda 1 squared, like this. Now, in addition to this result that we have, you have to remember that we also have a contribution of the kind minus lambda minus delta lambda. And it is something that I wrote at the beginning of this video here. And this contribution, let me also remind you, will come from something like this. You have to expand e to the minus s sub lambda 0, lambda 1. So in this case, the action depends on lambda 0 and lambda 1, because I have imagined that we have integrated out the low energy modes and also the high energy modes. This will be a function of phi. And then we have to subtract the counter terms. So there are some counter terms in the action, s of ct or superscript ct. This will be a function of phi. It will also depend on lambda 0 and lambda 1. And this action is defined exactly as we defined it in the previous lectures, but in this case it will also depend. I mean, the parameters delta m squared, delta z, and delta lambda will depend on lambda 0 and lambda 1, because we are assuming that we have integrated out the low energy modes and the high energy modes. And this dependence is showcased inside these parameters. That's what we have to think. And after we consider these corrections, we will let lambda 0 go to infinity and lambda 1 go to 0. We have to make a choice for delta lambda. In particular, delta lambda, we will choose it to be the following: 3 lambda squared divided by 32 pi squared natural log of lambda 0 squared divided by lambda 1 squared plus m squared minus 1. So this is capital lambda, remember that, whereas this is a lowercase lambda, but never mind. And let me also stress once more that this is a choice. It's just a choice. We have to choose it in such a way that the limits that we take will be finite. And so what we want to define is we want to define a new coupling, which is the effective lambda. So this effective lambda will be the parameter that we have, let's say, that arises when we consider also the quantum corrections. And this lambda f, or the effective lambda, we define it in particular minus lambda f. It will be minus lambda minus delta lambda. And remember that to this minus lambda minus delta lambda, we also have this correction here that we have calculated with a plus sign. So instead of writing all this expression, let me just call it C. And here I have to add C, just like this. Now we have chosen the expression for delta lambda and we have the expression for C. So there is just some algebra to do, and you can do the algebra. In particular, if you do the algebra, you get minus lambda plus 3 lambda squared divided by 32 pi squared. Then we have natural log of 1 plus m squared divided by lambda 0 squared minus lambda 1 squared divided by m squared plus lambda 1 squared plus m squared divided by m squared plus lambda 0 squared. So with the choice of delta lambda that we made, we can see now that as we let lambda 1 go to 0 and lambda 0 go to infinity, you can see basically that this logarithm will be the logarithm of 1, because this will go to 0, so we have log 1, natural log 1, which is 0. Since lambda 1 goes to 0, this term will be 0, and when lambda 0 goes to infinity, this also will be 0. So in the limit, we see that lambda f will be equal to lambda. So with this renormalization scheme, in the limit, we find that the pure quartic coupling in the quantum effective action coincides with the parameter lambda in the classical action. So this is a renormalization scheme, let me tell you once more, because it is related to some choices that we made in the parameters that we have. The renormalization theory, in particular the one related to the renormalization group that we saw in this course, allows us to understand how these corrections arise, right? Because we are integrating out some fields, or we are integrating out some modes, and we find corrections to the action that we see in the parameters that we have in our action. While at the beginning of the 20th century, these techniques were not completely understood. They were just regarded as some mathematical tricks that allowed to do computations in such a way that the results turned out to be right. The actual truth behind these mathematical quote-unquote tricks is that there is a theory, the theory of renormalization, that explains how and why we can do so.